All right, so we've been considering multi-degree of freedom structures, particularly right now we've been looking at an n degree of freedom system, as shown here. We went through and we found that we could express this equation of motion in terms of matrices, with a mass matrix, a stiffness matrix, and a damping matrix. And then we started working on modal analysis, which is the way that we solve these equations of motion. It's really the technique for decoupling them, and then solving them and then recoupling them. We gave out the steps for them, and then we were going through them, each step separately. We first start by formulating and solving an eigenvalue problem for the undamped, unforced system. That's exactly what we did here. We end up finding the characteristic equation for the natural frequencies, and then we found that there are going to be n natural frequencies, or where these natural frequencies are the square roots of the eigenvalues. We also only consider positive values for omega because negative frequency doesn't make any physical sense. I mean, mathematically it exists, but physically it doesn't make sense. Natural frequencies are ordered from the lowest to the highest, always. And then we went and determined the eigenvectors. From there we just went and substituted in the value for each eigenvalue, and then went and found the mode shapes. We said that the normal modes of vibration are the set of natural frequencies and mode shapes. So a mode of vibration has both a natural frequency and a mode shape. It cannot be defined by only one of those, it has to have both of them. And then we also said that they have arbitrary amplitude and they have the following orthogonality conditions, particularly that their mass and stiffness are orthogonal. And then you can compute a modal mass and modal stiffness, and then this allows you to find that natural frequency. We then started working on mass orthonormalization, which is one of the ways to find what this arbitrary constant should be. Actually, we were trying to find a very convenient amplitude for the mode shapes. We went through and we defined the orthonormalized mode shapes as phi I equal to alpha I times big xi. We then went and computed what these alpha i's should be, and we find that they're just square root of 1 over the modal mass. From there, we went and combined them together and formed the modal matrix. Just to be clear, this right here is a capital phi, and so the double underline here, there's a double underline that represents a matrix. And it satisfies the following orthogonality conditions, where big phi transpose times m phi is equal to the identity matrix, and phi transpose k times phi is equal to a diagonal matrix of the natural frequencies. Okay, and that brings us to step 3, which is where we'll start today. Oops, where did that go? There. To step 3, which is where we're going to start today. And we're going to start by defining modal coordinates, and then we're going to use them to decouple the equations of motion. So we're going to define a vector eta of t here, which is going to be equal to a collection of etas 1 through n, and each of these will be a modal coordinate. So each of them will describe the oscillations of a single mode of vibration, such that, and this is where we'll define what we'll call the modal transformation, the vector x of t, which contains all of the physical displacements, is equal to this modal matrix big phi times eta of t. The next dot is equal to big phi eta dot, and x double dot is equal to big phi times eta double dot. And we say that this is the modal transformation. Okay, so we're going to take our modal transformation and we're going to substitute that into the equation of motion. And this will give us the following. First, we'll have m times big phi eta double dot plus, and we're going to expand our damping matrix into its proportional form. So we'll just have an alpha m here plus a beta k. That's our damping matrix times phi eta dot plus the stiffness matrix times phi eta. That's then equal to some forcing vector f of t. We're then going to pre-multiply by big phi transpose. And this will give us phi transpose m phi times eta double dot plus alpha, and we're going to distribute the phi transpose here. So phi transpose m phi plus beta phi transpose k phi, all of that times eta dot, and plus phi transpose k phi eta equal to phi transpose f of t. The reason we did this is that we can find that phi transpose m, that's just the identity matrix. We have it in two places. And then phi transpose k phi, this is that diagonal matrix of the natural frequencies squared. For the forcing term, we'll call this a vector n of t. Thus, we'll find that this decomposes or breaks down into I eta double dot plus alpha I plus beta times this diagonal matrix of the natural frequencies squared. All that times eta dot plus a diagonal matrix omega I squared is eta equal to n of t. All right, the result of this is a set of n uncoupled second order ODEs of the form eta I double dot plus alpha plus beta omega I squared, all of that multiplied by eta I dot plus omega I squared eta I equal to ni of t, where this is just a single degree of freedom harmonic oscillator, damped harmonic oscillator with some forcing applied to it. And we have n of them, one for each mode of vibration. And by the way, you can also transform that damping into 2 zeta I, omega I, like what we had when we dealt with the single degree of freedom system. So the benefit of this modal analysis is that we take a highly coupled problem or set of equations, and we break them down into a set of uncoupled second-order ODEs, which we already know how to solve. We just now need to solve n of them, and then come back and combine them together, which we'll do in step 5. We also need to compute initial conditions, and we're going to rely back on our modal transformation. So start off by just saying that, let's say that the initial displacement, x, this is a vector as well still, x is 0 equal to some vectors of scalars. This must be equal to the modal matrix phi times eta at 0. Which means then that eta of 0 must be equal to the inverse of phi times x of 0, but we know that phi transpose m phi is equal to the identity matrix, and what this then implies is that phi inverse is equal to phi transpose m, such that for our initial conditions we'll get eta of 0 is equal to phi transpose m times x of 0, which we will just say is h. And then for initial velocities, we'll have eta dot of 0 equal to phi transpose m x dot of 0, and we'll say that's equal to g. Okay, so then the final modal equations are, we'll get eta I double dot plus 2 zeta I omega I eta I dot plus omega I squared times eta I equal to big N sub I of t. That's our equation of motion for the ith mode with initial conditions of eta I of 0 equal to hi and eta I dot of 0 equal to gi. Okay, so then, now that we have the final modal equations, we can then go and solve each of them. We'll find both a homogeneous and a particular solution for each modal equation. And you just solve it the same way that we did in chapter 2. You just got to do it n times now. So in that case, we'll find that the solution is that eta I of t is equal to e to the minus zeta I omega I t, all of that multiplied by hi times the cosine of omega di, that is the damped natural frequency of the ith mode, times t plus gi plus zeta I omega I hi, all of that divided by omega di times the sine of omega di t. That's our transient or free response. Yeah.
Does that say GI plus 1?
Here. That's a zeta. Yeah, so it should be gi plus zeta I omega I hi. So this is the free response. It's the same solution we found when we dealt with a damped harmonic oscillator. The difference now is that we have a lot of subscript i's, meaning that we've got to do this for every mode. And then there will be some particular solution. We'll just write that as eta sub pi. So that's the particular solution for the ith mode of vibration, and that's a function of time. Here we have what we'll call our free response. Over here is the particular solution, or the forced response. And omega sub di is equal to omega I times the square root of 1 minus zeta I squared. And here we're assuming that we have weak damping, meaning that zeta sub I is less than 1. Or the system is underdamped, we'll say. Of course, you could have critically damped, you could also have overdamped, and all of the stuff that we saw back in chapter 2 also applies here as well. Oh, and the particular solution also includes transient terms, which we can't compute unless we know what that applied force is. All right, the last step is that we are going to perform a modal superposition to form the final solution. And that simply means that we're going to go back to our modal transformation where x of t is equal to phi eta of t. We're going to use this to form a modal superposition, or we'll write out that xi of t is equal to little phi 1i times eta 1 of t. So this is the ith component of the first mode shape multiplied by the first modal coordinate in time, plus plus little phi I eta I of t, plus plus little phi ni times eta sub n of t. So that is the ith component of the ith mode shape multiplied by the ith modal coordinate in the middle there, and then the nth component of the ith mode shape multiplied by, it's the ith component of the nth mode shape multiplied by the nth modal coordinate eta n. And this is our solution. And this is what's known as modal superposition. So We find natural frequencies, mode shapes, mass orthonormalized. We then go and decouple the equations of motion. We solve the uncoupled equations, and then we use this modal superposition to form the final solution. And that's equation 34. All right, any questions before we go on to an example? All right. So we're going to consider a 2-degree of freedom example shown here. We're going to determine the response using modal analysis. We are given a non-zero initial conditions. Well, the initial displacement of x1 is non-zero, the velocity of it is 0, and the initial displacement of x2 is 0, and then we have a non-zero initial velocity for the second mass. So what we're going to do is first we're going to write out what the equations of motion are for this system shown here. Now generally we're going to give you the equations of motion. Well, some of the homeworks you may have to find the equation of motion. When you see a system that's just simple spring mass dampers like this, you can generally infer what the equations of motion are. You should definitely check your matrices to make sure they're symmetric as well. And you should also check to see if the system is classically damped, which we're going to talk about later. This system is proportionally damped. We'll see that in a moment. So our equation of motion is always mx double dot plus cx dot plus kx, and there's no forcing. And in this case, this x is equal to the vector x1, x2. This is always going to be true, but the matrices themselves may change. But the entries inside of them can differ. But regardless of what's inside each of these matrices, we're always going to formulate an equation of motion like this. So our mass matrix here, there's no inertial coupling terms here. Those generally arise through things like rotation. In this case, there's nothing that can lead to that. So we're going to get a diagonal mass matrix of, well, hold on a second. All right, it says that the mass of block 1 is 1, and the mass of block 2 is 2, but we actually need to flip these. We need to switch these. So forget about that, forget about that. This is a mass of 2, this is a mass of 1. Yeah. Okay, so then our mass matrix is 2, 0, 0, 1. The stiffness matrix K is equal to, looking at what the springs that are acting on mass 1, we have, well, a stiffness of 2 and a stiffness of 1. So the first entry here is going to be 3, and then the off-diagonal term will be minus 1 because of that coupling spring, and then minus 1 down there, and then lastly, we'll add the 1 and the 1 together to get 2. Then our damping matrix, we'll do something similar. We will get here 0.15 minus 0.05, minus 0.05, and 0.1 here, such that the damping matrix is equal to 0.05K, such that we do have a proportionally damped system and we can go about using classical normal mode theory, which is what we just went through. Yeah.
I'm sorry, I'm a little bit confused. Can you explain how you came to the entries in each of those matrices? I understand that you're adding up the different values for the dampers and springs, but I'm a bit confused about how you went about it.
Yeah. So let's look at that 3 right there. We have a stiffness of 2 here, a stiffness of 1 here. Each of those springs are going to add together and act on mass 1. This spring right here, the 1, it's also going to act on the second block as well. So we're going to get a minus 1 here. And if you were to come and write out what the spring forces are on block 1, you would find that it's going to be equal to 3x1 minus x2. That's what I've got this from. Likewise, if we take a look at, this is block 1, we do the same kind of analysis for block 2. We're going to look at what springs are acting on block 2, and we're going to ask which ones are coupled to another mass. We'll deal with the coupling first. And so this entry right here is going to always be multiplied by x1. And so we're going to look for what acts on, what couples block 2 to block 1, and that's this spring right here. Now what acts on block 2 is a summation of these two stiffness, or these two springs, or those two components. So in this case, for block 2, that force is going to be 2x2 minus x1. Does that make sense? And you can do Newton's method or Lagrange's equation, any of those, and you'll find that this is true. And so if you're not comfortable and you don't trust yourself, you just do the Lagrange equation. For a system like this, there's no crazy kinematics to deal with, and finding the energies will be relatively straightforward. We do the same type of analysis for the damping.
So block 1 is the object beforehand, then shouldn't be block 2. No. Because you say there is a 2 in the first and then 1 in the second.
Yeah.
So block 1 is technically block 2. Or block 1 is block 1.
Block 1 is block 1. I changed the mass of it.
Oh, okay.
Yeah, so
Okay.
all I did, in your notes, you'll see that this was 1 and this was a 2, and we just needed to switch the masses. Because that's the problem I solved, and it changes everything, and we've got 2 pages of calculations that we could redo. Sorry, it's 3 pages. So it's a lot to redo, which I don't mind redoing. It just means that next week, instead of 2 lectures, we'll have 3 lectures of content to cover through pre-recorded videos, because we don't have in-person class because I'm not here. So that's why we're going to change those masses and save some effort. So that means that this mass here still goes to that block. This mass here goes to that one. All right, any other questions? All right, we're going to continue. We're going to formulate and solve the eigenvalue problem for the undamped, and well, there's no forcing, so we don't care about that. So it's just the undamped system. In that case, our equation of motion here is mx double dot plus kx equal to 0. From here, we're going to provide an ansatz. We're going to say that our displacement x, little x, is equal to some big X, e to the j omega t. We are already assuming that the damping is weak here, or we have an underdamped system, because we're assuming a complex term here, meaning that there will be oscillations that arise. Real systems are typically underdamped, so this is a valid assumption. I've never seen a system that was critically damped or overdamped in like experimental testing, in all honesty. And things like steel, like if you make like a steel beam, the damping ratio of the first mode, which is always the highest, is around 0.1%. So it is very small, very weak. So this is a very reasonable assumption. Okay, so from here, we're going to plug our ansatz into our equation of motion, which will lead to the following: that minus omega squared m plus k times big X e to the j omega t, that's equal to 0. The only way for this to be true is, well, big X can be 0, but that means there's nothing interesting going on. That's just our trivial solution. And so the only way for this to be true is for the determinant of minus omega squared m plus k, that must be equal to 0. We'll write out the determinant here. We have minus 2 omega squared, that comes from the mass matrix, shown up there, plus 3 from the stiffness matrix. In the off-diagonal terms, we have minus 1 and minus 1. Then we'll have minus omega squared plus 1 in the last diagonal term, and that must be equal to 0.
What is the bottom right term, the plus 2 in the K matrix?
Yeah. Oof. We're lucky. That was this mistake here, not in my notes. Yeah, if we run into another mistake like that, then we're just going to have to redo the analysis. I mean, if we make it into like page 7 and there's a mistake, we're just going to have to recompute it at that point. Yeah.
I pointed out by that point.
Well, I think it would be in your benefit, because when I go to solve the exam, I'm going to solve it using software. So I'm going to have a guaranteed answer without any like mistakes. So I'm not saying that the exam is going to have any, be the example, but you're going to want the right answer so that when you're studying, you're not like, what the heck happened here?
Yeah.
And if it's a really tedious thing, then I'll go compute it outside class and come back. If it's something simple, then we can just resolve. All right, so if you compute the determinant here, you're going to get that minus 2 omega squared plus 3 minus omega squared plus 2 minus 1 equals 0. Oh, and that being said, for this class, you're going to solve this typically manually by hand, like homework problems and exam problems. And then later on, if we have time, we'll go over how to do this in like MATLAB or Mathematica or something, such that in the future, you don't need to do it by hand every single time. It's quite tedious to do this for something like 3 degrees of freedom or more. And when you're studying real systems, you're dealing with thousands of degrees of freedom, and you just use software. All right, anyway, moving on. We can compute this characteristic equation. It becomes 2 omega to the 4th minus 7 omega squared plus 5. That's equal to 0. We're then going to say that lambda is equal to omega squared and reduce this down to a quadratic equation, rather than a quartic equation, because we can solve the quadratic equation. In this case, we can also solve this quartic equation. You can't always solve every quartic equation, but we hopefully all know the formula for the quadratic equation. And if not, you should look it up. So we'll get here lambda squared minus 7 over 2. I'm dividing by 2 as well. Times lambda plus 5 over 2 equal to 0. From the quadratic formula, we'll find that lambda must be equal to 1/2 times the quantities 7 over 2 plus or minus square root of 49 over 4 minus 10 which ends up being 1/2 times 7 over 2 plus or minus square root of 9 over 4, which comes out to being 7 over 4 plus or minus 3 over 4. Such that lambda 1, which is always going to be the smallest one, so we'll have here, we're going to subtract the 3/4, and we'll get 4 over 4, or equal to 1. Tells us that omega 1, which is the square root of lambda 1, is equal to 1 radian per second. Although I think this system is dimensionless, so we won't include units. So we get omega 1 equal to 1. Then omega 2 is going to be where we add these two together. We'll start with lambda 2 equal to 10 over 4, which is equal to 5 over 2, such that omega 2 is equal to the square root of 5 over 2, and that is equal to 1.581. All right, now that we have the natural frequencies, we're then going to go and compute the mode shapes. We're going to do that by substituting in these eigenvalues, or the lambdas. Starting with lambda 1. Remember, lambda is equal to omega squared, so we'll plug this in, we'll get 2, minus 2 times 1 plus 3, minus 1 on the diagonal, minus 1 here, minus 1 plus 2 here, multiply by x, 1, 1, x, 1, 2. So the first and second components of the first mode shape, and this must be equal to our 0 vector. It simplifies down to 1 minus 1 minus 1, 1 times x11, x12 equal to 0, 0. Then from here, you can solve this. You'll get two equations. The first one is x11 minus x12 equal to 0. And then the second one is x12 minus x11 equal to 0. And surprise, these two equations are the same equation. Meaning that we only have one equation but two unknowns, and thus we cannot solve for it uniquely. We'll find that x11 is equal to x12. That's our only solution. So what that means is that, like I said, we have two unknowns but only one equation. That means our system is degenerate. And x1, x11, and x12 can take any value. And so this is what I mean by the mode shape can be scaled by any value. So we'll just pick something simple and we'll say here that x11 is equal to 1. That's just a simple choice. And then our mode shape, x1 is equal to 1, 1. And this is what we'll call the in-phase mode. And it's in phase because both masses move together in the same, with the same phase. In fact, it's the same amplitude in this case. We're going to do the same thing for lambda 2, which is equal to 5 over 2. In this case, we're going to plug this in. We'll get minus 2 times 5 divided by 2 plus 3 minus 1 minus 5 over 2 plus 2. Oops. In this case, multiplied by x21, x22, that's our second mode shape and the two components of it, equal to 0, 0. So this becomes minus 2, minus 1, minus 1, minus 1/2 here. x21, x22 equal to 0, 0. From here we'll find two equations, minus 2x21 minus x22 equal to 0, and minus x21 minus 1/2 x22, and again we find that these two equations are the same. And specifically we'll find here that x22 is equal to minus 2x1, x21. Yeah.
Should the 5 over 2 be squared? Is that what you're-
It should not be squared because if we come back,
I thought earlier it was omega squared.
you're right, but lambda is equal to omega squared.
Okay.
So that's the difference. And omega, the natural frequency was the square root of 5 over 2.
Right.
So that's where that went. So you were not wrong, but lambda and omega are not the same. That's the difference. Okay, so this is now just the same situation as mode 1. And it's always true. You always end up with, well, if you have you end up with n degrees of freedom, you have n minus 1 equations, so there'll always be one that is arbitrary. Hence why you can always arbitrarily scale a mode shape and it remains valid. So here we can say that x21 is equal to 1, and then we'll get that x22 is equal to minus 2, and that's our mode shape, big X2 equal to 1 minus 2, and this is known as the out of phase mode. Because the two masses move in opposite directions of each other or out of phase of each other. And we'll see here the modes of vibration. We're going to have two of them. First, omega 1 equals 1. Big X1 equals, I'm going to throw in here an alpha, just to arbitrarily scale them. Alpha times the vector 1, 1 transposed, because these should be a column vector. Then our second mode has omega 2 equal to square root 5 over 2. X2 equal to beta. That's our scaling coefficient there. And 1 minus 2 transposed. And those are the modes of vibration, the natural frequency and their associated mode shape. Yeah.
You said out of phase mode. How do you know it's in phase or out of phase mode?
So for a 2 degree of freedom system, you can tell because of the signs of the two masses. So for the first mode, they both have the same sign, and they could both be negative, but they're both going to move together in the same direction. That's what the in phase means. Now, out of phase, they're moving in opposite directions. So if block 1 moves to the right, block 2 is going to move to the left, and then they're going to switch positions and move in the opposite direction. That's what it is. For higher degree of freedom systems, in phase, out of phase kind of breaks down in general. And you just got to look at what the mode shapes are doing and see what's happening. And we'll see some examples of mode shapes for more complicated systems in general. Okay. So we can also draw our mode shapes. And if we were to do that, we would simply, here's our spring. If we wanted to just draw mode shape 1 here, we would simply say this is V11, X11, X12, and we could come and draw the reference position as well. I don't think I asked you to plot any of these or sketch mode shapes, but you can just sketch what these are and indicate their displacements. All right, we are going to move on and deal with mass orthonormalization now, and then we'll move on and be able to define the modal coordinates and then decouple our equations of motion. Okay, so we are going to let here V1 equal alpha 1, big X1, and we're going to forget about the alpha and beta that I put up there in the modes of vibration. We're just going to use the ones that we found numerically. And our phi2 is going to be equal to an alpha 2 x2, and then we're going to require that phi I transpose m, phi I we're going to require that equals to 1. For our first mode shape, this will end up becoming, if we plug in V1, we'll get alpha 1 squared x1 transpose m x1 equal to 1, such that alpha 1 is equal to the square root of 1 divided by x1 transpose m x1. So x1 transpose m x1 is equal to 1, 1 multiplied by 2, 0, 0, 1 times 1, 1, and that's equal to 3. Such that alpha 1 becomes equal to the square root of 1 over 3, which is equal to 0.5774. And then V1 is then equal to 0.5774 and 0.5774. We do the same process for phi2. In this case, we'll get here alpha 2 squared x2 transpose m x2 equal to 1. This means that alpha 2 is equal to the square root of 1 over x2 transpose m x2. And this turns out to be the square root of 1 over 6, or equal to 0.4083, such that phi2 is equal to, we'll put it right here, phi2 is equal to 0.4083, and then minus double that, or 0.8165. And then we can form the mass orthonormalized modal matrix. Which is going to be capital Phi equal to the matrix 0.5774 and 0.5774. That's our first mode shape, and then 0.4083 minus 0.8165. Ooh. Okay, once we've defined our modal matrix, we can then go and use it to, we'll define modal coordinates, and then we can use that to decouple the equations of motion. So we're going to let our x vector be equal to phi eta, which will then tell us that x dot is equal to phi eta dot, and x double dot is equal to phi eta double dot. We're going to substitute that into our equation of motion. To our equation of motion, and pre-multiply pre-multiplied by phi transpose. It's going to give us phi transpose M, phi eta double dot plus phi transpose C phi eta dot plus phi transpose K phi eta, fortunately equal to 0 because there was no forcing. This first term here, this is going to be the identity matrix. We said that C was proportional to our stiffness matrix. So we're going to get here 0.05 times the diagonal matrix of omega I squared. And over here, for the stiffness matrix, we're just going to get the diagonal matrix of the natural frequency squared. And then from here, what we'll find, if you go and do this, you'll find that we get two equations of motion, eta 1 double dot plus 0.05 eta 1 dot plus eta 1 equal to 0. And then eta 2 double dot plus 0.125 eta 2 dot plus 5/2 eta 2 equal to 0. For the initial conditions, we'll find that eta 0 is equal to phi transpose M x0. Eta dot of 0 is equal to phi transpose M x dot of 0. We'll get eta 1 of 0, eta 2 of 0. This is equal to that phi transpose 0.5774, 0.5774, 0.4083 minus 0.8165. This is 2001 times 0.10. This is equal to 0.1155 and 0.0817. We do the same thing for the initial velocities. And that was 0.1. It's equal to 0.5774 minus 0.8165. And in that blank space, we just have the same as what it's above. Okay, so we have two equations of motion. We'll have eta 1 double dot plus 0.05 eta 1 plus eta 1 equal to 0, with eta 1 of 0 equal to 0.1155 and then eta 1 dot of 0 equal to 0.5774. That's our first equation of motion. Our second one is eta 2 double dot plus 0.125 eta 2 dot, I missed the dot up here, plus 5 over 2 eta 2 equal to 0. With eta 2 of 0 equal to 0.0817. Eta 2 dot of 0 equal to minus 0.8165. Okay, from here you can go and solve these two equations. You'll compute the zeta and the omega, or you know what omega I is, but you'll compute the damped natural frequency and the damping ratio zeta for each of them. You can combine them together and you'll find that eta 1 of t is equal to 0.1155 times e to the minus 0.025 t. All of that multiplied by the cosine of 0.9997 t plus 5.026 times the sine of 0.9997 t. That's the response of the first mode. For the second mode, we get eta 2 of t equal to 0.0817 e to the minus 0.0625 t multiplied by the cosine of 1.57799 t plus, actually this is a minus 6.286 times the sine of 1.5799 t, and that is the response of each mode. From here, we can go and perform the modal superposition, where x of t is equal to phi, big phi, times eta of t. And I've already given you, or left the solution in the notes for you, so we don't have to write that out. But you'll see that the modal response, or the etas, appears in each of the degrees of freedom in their total response. So for example, right here we get mode 1, and then beneath that we'll get mode 2 participating. All right, so I've gone ahead and I've plotted the modal responses on the left here, which you'll see that they only have a single frequency of oscillation. And then on the right is the superposition and the physical displacement of each block, which is a modal superposition of the individual mode responses. Okay. MATLAB code is given there. If you want a copy, you can download it from the QR code. For the rest of the class, we're going to take a look at some mode shapes from real systems out there in the world. All of them come from my own research. So the first one is this model fighter jet that we've built and have in our lab. We don't have this one. We have one just like this one. It's just a steel cylinder with steel plates combined to it, and it has the geometry and therefore exhibits the same mode shapes of a real fighter craft. The wing profile is based on the F-16 here. We took this system, we built what's known as a finite element model, shown here. You basically discretize it down into little blocks, and then you use those blocks as a way to compute the equations of motion and then use that to find the mode shapes. And these are what I think I have 12 flexible mode shapes here. In general, there are an infinite number of these mode shapes. For that particular system, they would be 19,810 times 6, because that's how many degrees of freedom there were. But in general, we really don't care about the first few flexible modes. First one here, both of the wings are going to move up and down in your typical flapping, and they're going to move simultaneously. The second one, the wings are actually going to move opposite of each other. So this would be, your first one would be in phase, the second would be considered an out of phase in this case. And then the third and the fourth are actually twisting modes or torsional modes in this system. The reference is listed here if you're interested. Here's a wind tunnel fighter jet model that we've been working on with NASA, shown here. This is just what it looks like. And we also include like weapons and so forth on that. There's a finite element model for this, and these are what these mode shapes look like. Very similar to the previous fighter jet as well. Let me see what else we have in here. Here's a bolted beam, so two beams combined with 3 bolts in the center of them. In this case, this system there was a device attached right here, and that allowed us to shake or vibrate this system. We had an accelerometer here. And then we actually use what's known as digital image correlation to film this entire structure, and we use that to compute the mode shapes of the beam as shown here. And so these are the first 3 flexible modes of this particular beam. So you can not only compute them using computational models, you can also measure these things experimentally as well. And then the last one I wanted to discuss, this is one where we have 3 axial rods, and they're connected by a bolt or a threaded interface. And in this research, we're studying how these things loosen or how the tension or the torque in that interface changes over time. And so we show and find that the mode shapes depend on the torque or the tension inside them. And so we're able to plot here how these mode shapes change as a function of the torque in the joints, as shown here. So anyway, you're not going to be expected to do anything like this. Of course, these come from research papers that are like maybe 5 years old, if not less. But I just wanted to give you some examples. On Wednesday, we're going to cover damping. We'll talk about rigid body modes. And we'll do another example. And then next week, we'll do harmonic excitation. All right. You guys have a good day.